Welcome everybody to the screencast for the binomial distribution. Today we're going to be covering some mathematical review. We'll discuss what a permutation is. I'll remind you about factorials and factorial notation. Choose notation, which if you haven't seen that before will probably sound a little bit weird. We'll discuss binomial distributions, what they mean, what the formula is, and how to do calculations in R. We'll discuss some of the characteristics of the binomial distribution, and we'll have a little bit of an example, or a few examples. Okay, so in a review, here's the review. A permutation is an arrangement of items. So if I had, and again we think of these things in terms of sets mostly, right? If I had this set A, B, and C, so I had 3 letters, and I wanted to think of all the different ways I could arrange them, each of those arrangements would be a permutation. And so BAC, and I'm using the commas just to make things clear, is a permutation of ABC. There are 6 of them. ABC, ACB, BAC, BCA, CAB, and CAB and CBA. So those are the only 6 ways you can arrange A, B, and C without using repeats. So in factorial, now you know there's a formula for it. I'm sure you've all seen this before. But anytime you hear the word factorial, I want you to think of that as being the number of permutations of n objects. So if somebody says, what's the number of ways to arrange 3 items, or 3 distinct objects, in the back of your head, you would say 3 factorial. And if somebody said, how many permutations are there of 10 objects, in the back of your head, you would say 10 factorial. So that's like the first idea, right? Anytime you hear the word factorial, you are counting arrangements in some way. So, to denote that something is a factorial, we just follow it with an exclamation point. So you don't read that as 3 exclamation point, you read that as 3 factorial. And the formula is actually quite simple. You just start writing all the numbers down, decreasing them by 1 every time. And I like to go all the way down to a 1. Even though multiplying by a 1 doesn't change anything, that means that 4 factorial is going to have 1, 2, 3, 4 terms in it. 4 times 3 times 2 times 1. So 4 times 3 is 24. 24 times 2 is 48. 4 factorial is 48. Oh, it looks like I cut off a little bit at the bottom. That's okay, I have it on a different slide too. How many ways can 5 letters be arranged? Of course, those are distinct letters, and that's 5 factorial. And if you think about it, letter 1, letter 2, letter 3, letter 4, letter 5, you have 5 choices for the first letter, 4 for the second, 3 for the third, 2, and then you don't really have any choice for the last letter. 5 times 4 times 3 times 2 times 1. And you saw that here, right? So we had 3 choices for the first letter, an A, a B, or a C. After we had chosen A to be our first letter, we had 2 choices for the second letter, a B or a C, and that locked in the third letter. When our first letter was B, we had 2 choices for the second letter, A and C. Now those choices were different than they were in the previous scenario, but that's cool. And then once we'd chosen our second letter, everything else was locked into place. So 3 times 2 times 1 is 6. Okay, so that's permutations. And there's a special thing, 0 factorial, the number of ways you can arrange 0 objects, we still consider that to be 1. That makes all the formulas work out nicely, and it makes a certain amount of sense, right? How many ways can you not arrange things? Exactly 1. Okay, now we have this different idea. So let's think about this scenario. How many teams of size 3 can be made from a pool of 5 candidates? So you have 5 individuals to choose from, and you're picking 3. And of course, in teams, nobody cares about the order, right? You're all just in the team or you're not, so that makes it like a set. So in other words, how many subsets of size 3, if you want to think of it that way. So we'll let A, B, C, D, and E be the pool, just because it's easy to think about letters, I think. So what are our possible teams? We could have A, B, and C. We could have A, B, and D. We could have A, B, and E. And again, order doesn't matter, so A, C, and B would be the same as A, B, and C, and so on. We could also have A, C, and D, or A, C, and E, and A, D, and E. So I've exhausted all the possibilities for the different teams I could have, which have A in them. In this first set, you'll see I had A and B, and then here I had A and C, but not one of these other ones that I've already looked at, and A and D. So now that A is not in the running anymore, I could have a B, C, and D, or B, C, and E. This encompasses everything where I have a B and a C on the team, and then a B and a D on the team, but not one I've previously seen before. And then C, D, and E is all that's left by the time I get to the last one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so there are 10 teams of size 3 that can be made from a pool of 5 candidates. So the notation for that, and again, just like with that factorial notation, I want you to start thinking of it anytime you see there's a number on top, there's a smaller number on the bottom, there is no horizontal line. That's pronounced 5 choose 3. And again, you should think of that as how many teams of size 3 can be built from a pool of 5 candidates. So for small values, you don't need a formula. You can figure them out directly, like we did here. Now I want to point out that whether the pool involved letters, A, B, C, D, and E, or if the pool was numbers 1, 2, 3, 4, and 5, the pattern's still the same, right? The actual members themselves, as long as they're all distinct, don't matter. So there are still just 10 ways to make a team of size 3 from a pool of size 5, no matter how I'm labeling the candidates. Now, I want to ask you a question, which is kind of neat, I think, because on the surface it looks quite different, but it's actually related to what we've just noticed. So, how many distinct words can be made using exactly 3 S's and 2 F's? So, for example, SSSFF has 3 S's and 2 F's. SSFSF, SSFFS, and so on. And you've probably noticed that I've arranged them in sort of a graphical pattern that's somewhat similar to what we saw both here and over here. And so what I want to draw your attention to is a word, and here I only have 2 choices of letters. That's what makes this work, and that's going to matter to us because that's what we primarily care about, and you'll see why in a bit. It has 3 S's in it. And here I have S in position 1, in position 2, and position 3. Then I have F's in position 4 and position 5. So you could almost think of this as the positions are specifying which of the locations are in team S. Right? So 1, 2, and 3 are where my S's are. 1, 2, and 4 are where these S's are. 1, 2, and 5 are where these S's are. So I hope you see the pattern. And so the number of words that we can spell with exactly 3 S's and exactly 2 F's is the number of ways we can make a team of size 3 from a pool of 5 candidates. It's 5 choose 3. So said more colloquially, how many ways can I choose 3 from 5? So that's a little bit of a shorthand, and if you're not used to hearing it, it might sound a little bit awkward, but it's pretty common for people to say it that way. And so the answer to this question is exactly the same as what it was before. 5 choose 3 is 10. And if you're really kind of thinking about this, and by the way, if you don't, that's cool too, instead of choosing where the S's go, I could have chosen where the F's go, and that would have been equivalent. So 5 choose 3 is the same as 5 choose 2, which is kind of an interesting fact. Some of you may have seen that before. Okay, so you have this idea, and in small situations, we can just list them all out. In larger situations, it becomes a little bit trickier. If anyone's interested, ask during one of the Zoom sessions, and I'll explain what exactly is going on here. But for those of you that just like to have the formulas, n choose k is n factorial divided by k factorial divided by n minus k factorial. So there's a lot of symbols in there, but if you start looking at the patterns and what those represent, it actually isn't that bad. So what happens? I have a 5 and a 3, and there's no horizontal line. So I have a 5, and I'm going to put a horizontal line in, and a 3. I put exclamation points on both of them. That's my n factorial and my k factorial. And then I just choose whatever number I need to add up to the top. So 3 factorial needs a 2 to get to 5. So 5 factorial divided by 3 factorial times 2 factorial. So 5 factorial is 5 times 4 times 3 times 2 times 1, 20, 60, 120. 3 factorial is 3 times 2 times 1. 2 factorial is 2 times 1. There's my 3 factorial, there's my 2 factorial. It's magic, but everything will always cancel correctly and you'll get a whole number. 120 divided by 12 is 10. 5 choose 3 is 10, which we knew, but that's kind of cool. Actually, just for completeness sake, some of you can just kind of put your fingers in your ears if you don't want to hear this, but if I wanted to count the number of ways I could choose 3 from 5, right? You could think about arranging, actually no, I'm not even going to go there. I think it's cool, but if you're curious, ask me. So the other formula, which is equivalent, is, and again, writing it out formally makes it look a little bit tricky. You just start with the first number, and you just go, maybe 3 was kind of a bad choice here, but you have however many terms, whatever the bottom number is how many you have. So I have 1, 2, and 3. And the bottom starts with 3, 2, and 1. And that will also always work. And that's often sometimes faster. So you see the 3's cancel, get a 2 canceling here, 5 times 2 is 10. So 5 choose 2, I start at 5. I just have 2 terms in the numerator, and then my 2 factorial gives me 2 terms in the denominator. 20 divided by 2 is 10 again. Like I said, 5 choose 2 does equal 5 choose 3. Okay, there's a few special rules to be aware of. I already mentioned that 0 factorial is 1. Anything choose 0, including 0 choose 0, is 1. We define it that way. But it turns out that works out really nicely with the 0 factorial rule, right? So 5 over 0, which is usually illegal, but once I put the factorial on it, it's a 1 now. And then whatever else I need to get up to 5. So 0 factorial is 1, so I don't care about it. 5 factorial and 5 factorial, it all cancels out to be 1. So one other thing that's worth paying attention to, because it will come up, is anything other than, oh, hang on a sec. Anything other than 0 to the power of 0 is 1. All right, so 2 to the power of 0, that's 1. Minus 3 to the power of 0, that's 1, and so on and so forth. Okay, now we're working our way up to this binomial distribution. So I want to think about the multiplication rule, and I want to think about it in terms of a sequence of independent trials. So a trial can result in success or failure. So for example, maybe I want a 1 when I roll a die, and I'm looking for a 1, and if I get anything else, it's a failure, and if I get a 1, it's a success. Or maybe I flip a coin, and I'm looking for heads. So getting a head would be success, getting tails would be fail, right? And let's suppose the probability of success is p, where I'm not specifying that number, but it's a probability, so it must be between 0 and 1. So I could ask, what is the probability of getting SSFSF if they are independent trials? So because they're independent, I can just focus on each trial alone and multiply the things together. So the probability of SSFSF is the probability of the first is S times the probability of the second is S times the probability of the third is F times the probability of the fourth is S times the probability of the fifth is F. P times 1 minus P times 1 minus P. And if I group, because I'm allowed to group, that's P cubed times 1 minus P squared. In other words, P to the number of successes times 1 minus P to the power of the number of failures. So that's going to be important to us. So again, if you think about it, so if the probability of success is 25% and the probability of failure is 0.5%, the probability of SSFSF is 0.25 to the 3 successes, times failure, 1 minus 0.25, 0.75, to the number of failures, 2. That's about 0.0088. Now, this is where it gets interesting. What is the probability of getting a sequence with exactly 3 S's in it? Right? So I can tell you the probability of getting SSFSF is 0.25 to the power of 3 times 0.75 to the power of 2. the probability of getting S, F, S, S, F, a different sequence, is the same thing, right? I still have 3 S's and 2 F's in it, and the order isn't going to matter. So all I need to do is figure out how many sequences with exactly 3 S's and 2 F's in it exist. Oh, but we know that, right? So 3 S's out of 5 total is 5 choose 3, and then each of those has a probability of 0.25 cubed times 0.75 squared. So 5 choose 3, as you'll recall, is 10, times multiplying these things out, which is 0.0088, is about 0.088. 0.0, yes. Okay, so now we have all of the mathematical review in place. So a binomial distribution is discrete, takes on very specific values, and it's finite. It has 2 parameters. So what are those parameters? A number of trials, n, that's fixed. The trials all have to be independent, so knowing what happens on one gives us no information about the others. Every trial is dichotomous. It either results in success or failure. The probability of success on each trial is always p. It's always the same thing, and I'm using p to indicate that. And I count the number of successes. So then the parameters in this distribution are the number of trials. The probability of success on each trial is p, so my notation, if I have a random variable x, is tilde, which tells you the thing on the left is the random variable, the thing on the right is the distribution. It's a binomial distribution. The first number is how many trials. The second number is the probability of success per trial. So a simple example, flip a coin 20 times and count the number of heads. So the number of trials is 20, right? I have 20 chances to count something, and I'm considering a count to be a success. Each coin flip is independent of the others. So I've checked off this box, I've checked off that box. Each coin flip results in heads, which is what I want to count, or tails. So there's my dichotomous outcome. And again, bear in mind, if I was rolling a die, if I was counting the number of ones, a 1 would be success and everything else would be a failure. So it's still okay to use a die for that. It's just whether you get something you count or not. Each flip has the same probability of getting heads, 50%, and what I'm doing is counting them up. So those are the 5 conditions that we need for something to be a binomial distribution. And these show up hello. These things show up all over the place. Now, as you've probably figured out, there is a probability formula for these. So the probability formula tends to be a little bit off-putting the first time you see it. But as always, P for probability, some kind of an event inside the parentheses, in this case, the probability of getting a specific result. And it's n choose k, the number of ways that you can get exactly k successes, because remember you're counting, right, out of the n trials. And then each individual configuration, p to the k, 1 minus p to the n minus k. So let's make this concrete. Pat plays a fair game with a 5% chance of winning. Pat plays 5 games. The games are independent of each other. What is the probability that Pat wins exactly 3 games? So we're going to let x be the number of games that Pat wins. That's a numeric result of a random process. That is a random variable. So the distribution of x is binomial 5, 3. Let's make sure. Number of trials. Does it change? Nope, Pat's playing 5 games. Okay, n is 5. Awesome. The games are independent of each other. We have independence. That's great. The probability is 5% every time, so it's a constant probability, and we have our value of p, and that shouldn't be 3. That should be 0.05. I'll fix that in just a second. So I have the constant probability. See, the games are independent. I lost track of where I was at, and we're counting the number of games because we want to know the probability of Pat winning exactly 3. So the probability of winning 3 games is the probability that x is equal to 3. Plugging everything into the formula, 5 choose 3, 0.05, that's the probability of success to the power of 3, times 0.95, the per trial probability of failure squared for the 2 failures. And that comes out to about 0.001. Now, on the other hand, and this might surprise you, given there's only a 5% chance of winning, what is the probability that Pat wins at least once out of 5 games? So this is a probability question, and it's easier to calculate the probability of losing all the games and subtracting that from 1. So we'll do that. The probability that x is greater than or equal to 1 is 1 minus the probability that x is 0. So that's going to be 1 minus 5 choose 0. And remember, anytime you choose something with 0, it's a 1. 0.5 to the 0. 0.05 to the 0. Ooh, riddled with errors. That's a 1. 0.95 to the power of 5. 1 minus 1 times 1 times 0.774, about 0.336. So there's still a 33.6% chance that Pat's going to win at least once, even though the odds of winning aren't particularly good. So that's kind of cool, I think. And hang on a second before I go on, I'm going to fix this. Great, thanks. All right, now, we want to use R to do this rather than having to go through these calculations ourselves, but you should be able to do various, choose calculations. And if you want practice, these Zoom sessions would be a great time to ask me about them. So the R command dbinom can be used to calculate these probabilities. So if x is binomial n comma p, then the probability that x is equal to k is dbinom k comma n comma p. So suppose x has a binomial distribution where n is 100 and the probability of success is 0.1. What is the probability that x equals 15? So we're asking, what is the probability that x equals 15? So k is 15. There's our 15. Now n was 100 and p was 0.1. And so R just calculates it for us directly. Now you could do it yourself if you want, right? You could do 100. Let me erase that. The probability that x equals 15 out of the 100 options, right? The 100 trials. I want to know where the 15 successes are. Each one of those successes is probability of 0.1. So the failures are 90%, and there should be 85 of those. So 100 factorial, your calculator would break on that. So you'd want to use the 100 times 99 times 98. And I would usually start canceling things out myself by hand just to make it a little bit easier. But when all is said and done, what we would get is about 0.03268. Now, here's a different question. Suppose that x has a binomial distribution. Same setup. What is the probability that x is greater than 15? So here's where you can get an exact answer using R, and you wouldn't want to do this by hand. So in R, I can use a colon to represent a range of values. So 16 up through 100 is 16 colon 100. And so if I didn't have that sum on the outside, this would list all 85 of those different possibilities. 16, 17, 18, 19, 20, 21, all the way up to 100. Right? So I put the probability value, the results I'm interested in. I put the parameter for n, I put the parameter for p. This would be a whole big long bunch of them, and then I use sum to add them up. And you see, it's actually pretty close to the probability of getting 15 exactly. 0.0398, so about 4%. Probability that x is greater than 15 under this scenario is about 4%. Now, I want to give you some examples about describing the situation that we will, or describing the distribution that we will care about a lot more later. So I'm going to have these in different slides in the future. So for now, I'm including them to make this sort of self-contained. So remember, x is a random variable. So there is an expectation value or an expected value, also known as the mean. There's a variance and there's a standard deviation. The expected value of x is the product of the two parameters, n times p. The variance is that same thing times 1 minus p. And the standard deviation is the square root of the variance, as it always is. So if you can find the variance, just take the square root and you get the standard deviation. Again, I'll show examples on a different set of slides, but I wanted all of this in one place, so if you're reviewing in the future, you can see everything at once. Now, what this is kind of related to, and I do want to show you one example because it's so important we're going to be dealing with it, is something that's called the normal approximation to the binomial. So remember, when we had a normal distribution, it had a mean and a standard deviation. So I hope it doesn't surprise you that if you're approximating a binomial distribution, you're going to put in the binomial distribution's mean and the binomial distribution's standard deviation. So those are going to plug into the normal distribution. So the tilde means has the distribution. So if x has a binomial distribution, the a means approximate. So if x is binomially distributed with parameters n and p, then x is approximately normal. And the larger n gets, the more accurate that approximation becomes. Approximately normal with a mean of n times p and a standard deviation of the square root of n times p times 1 minus p. And it turns out, and this is like super cool, p hat, which again we'll talk a lot more about in the next slide deck. Again, this is just to have everything all in one place. P hat is a sample proportion, and it's approximately normal, and its mean is the true value. Notice to go from a count to a proportion, I just divide by n. So dividing by n gets rid of that. There's my p. Dividing a square root with an n inside of it by n puts the square root of n on the bottom, and it cancels it out on the top. And so if your algebra is good, that's also pretty obvious. All right, now let's use this normal approximation to the binomial just so you can get an example of it. So suppose that x is a binomial distribution with n of 100 and p of 0.10. What is the approximate probability that x is greater than 15? And so the word approximate is kind of the key thing here. So approximate suggests we use the normal approximation. So what you do is you figure out the mean and the standard deviation. So the mean is n times p, 100 times 0.10. The standard deviation is the square root of, oops, it looks like I'm missing a term here. Let me pause. There we go, that's a little bit better. So I had I was missing a term in there. So we're taking the square root of n times p times 1 minus p. That comes out to being 3. So x is approximately normal with a mean of 10 and a standard deviation of 3. So the probability that x is greater than 15 is the probability that z is greater than 15 minus 10 divided by 3, right? Because what is this? This is a z-score question now. This is now a normal distribution question. And so once you have your normal thing here, now all the stuff from table A is good to go. There's nothing any different from anything you've ever done before. So this is an upper tail problem. So it's the probability that z is greater than 1.67, which is 1 minus the probability that z is less than or equal to 1.67. I do a table A lookup on 1.67. I get 0.9525. I take the difference, 0.0475. And if you compare to the value that we came up with earlier, which was 0.04, I say approximately, that's probably a little misleading. That's what it rounded to. You see that they're actually not too terribly far off. And so as n becomes large, the normal distribution becomes a better, becomes a reasonable approximation. And so what's happening is something called the central limit theorem. And we'll talk about that in another slide deck. All right, thanks for listening.